Okay, good morning students. For in today's session we will discuss about the FFT algorithm. So FFT, so what is FFT? Fast Fourier transform. Fast Fourier transform. So before discussing the FFT, so what are the difficulties? Because it is DFT computation only. DFT computation only we are doing. Last session, that last two sessions, how to compute the DFTs, endpoint DFTs using that computation method and matrix method we have seen. Now, what are the difficulties? What are the difficulties in DFT? Okay, what are the difficulties in DFT? Because the direct implementation of DFT requires large number of multiplication. The direct implementation requires large number of multiplications, additions and trigonometric functions. Large number of multiplication, additions and the trigonometric functions. In real time, it is not practical to handle a large number of input samples. In real time, it is not practical. It is not practical to handle large number of input samples. So for endpoint, for example, for endpoint DFT, the direct computations, it requires n squared multiplications and n into n minus 1 additions are required. So to reduce the time required to compute the DFT, the FFT is developed. So the FFT is developed by eliminating the redundant functions, redundant calculations. So the FFT was developed by eliminating the redundant functions. Redundant calculations in the direct implementation of DFT. So what are the difficulties in DFT? So that the FFT fast Fourier transform is developed. So the FFT is basically based on decimation process. It is based on, the FFT is based on decimation process. Decimation means dividing. You are dividing the decimating process. So the decimating your DFT, the endpoint DFT is decomposed into smaller DFTs. So the endpoint DFT is decomposed into smaller DFTs. Smaller DFTs, decimated. Okay. So this decimation can be Okay, this decimation process can be performed either in the, this FFT can be performed either in the time domain, okay, either in the time domain or the decimation in the frequency domain. So it can be performed either in the time domain or it can be performed in the frequency domain. Frequency domain. So the endpoint DFT is divided into, is decimated into 2, for example 2 n by 2 DFT, again which will be decomposed into 2 n by 4 DFT, this again divided into 2 n by 4. For example, if it is n is equal to 8, the 8 by 2 it will be 4 and 4. It is decimated into 2 4-point DFT, and again this 4-point DFT is divided into 2 n by 4, 8 by 4. So again 2, this will be 2, this will be 2, this will be 2. So 8 is divided into 2 4, again the 4 is divided into 2 point, 2 point, again it is divided into 2. So whatever the end point, okay, we are decimating until you get the 2-point DFT. This is a 2-point basic 2-point DFT structure. So how to represent this 2-point DFT butterfly structure, we will see. So this FFT fast Fourier transform can be performed either in time domain or in frequency domain. So that is a time domain. So decimation in time domain FFT, okay, or the decimation in frequency FFT. Okay, we are dividing the endpoint into 2, the means the samples, endpoint samples splitting into even and odd. So even and odd samples, for example the input sequence x of n. Okay, the samples are divided into x of n, the endpoint DFT sequence. So 2 n by 2 points DFTs by splitting the input samples into 2 n by 2 DFTs. Okay, even, this is even sample, you can say this is a even sample, this is odd sample. The endpoint 8-point DFT, the x of n input samples, the input samples, okay, for example input samples. So x of n is equal to x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7, x of 7. Okay, these are the position. So these are samples. This is 0th position. This is a position I am saying. The data may be whatever. For example, 1, 2, 3, 4, 4, 3, 2, 1. For example, n is equal to 8 point. Okay. So this endpoint samples. So this n is equal to 8 is divided into 2 even and odd samples. Again this will be divided into, this is even, this is odd. Again this is divided into 2 n by 4 even and odd. With respect to the position I am saying, this is even, this is odd. So you have to decimate in this way, the same way you have to decimate 2 n by 4. Okay, first even and odd 2 n by 2. Okay, the 2 n by 2 DFTs are further divided into, in the same way, into 4 n by 4 point DFT, and this decomposition process continues until 2-point DFTs are obtained. This is a 2-point DFTs are obtained. Okay, until 2-point DFTs are obtained. So what is the DFT equation, you know? So mathematically we will derive how it was. First we will understand the concepts. So x of 0. So even and odd samples with respect to the positions, if you say, so first endpoint is given into x of even and odd with respect to position. I am saying x of 0, x of 2 and x of 4 and x of 6 and even this is another color I will take, x of with respect to position x of 1, sorry, this x of 1 with x of 3, x of 5, x of 7. So the x of n sequence are divided into the 8 point is divided into 2 4 point. Again this 2n by 2, this is odd and even part. This is even. See, this is even. You have splitted the x of n into even and odd. Again this even is divided into 2n by 2. So this is n by 2. 8 point is divided into 4 point, even and odd. Again this even is divided into, this even is divided into n by 4. Okay, so n by 4, 8 by 4, 2 point. So now this position, if you see the position here, will you imagine just this is 0th position, this is the first position, this is the second position, this is the third position. So now again you divide into 2 even and odd. So now the next stage will be, what is the next stage decomposition? X of even position will take first, x of 0 and x of 4, and this will be first odd position will be x of odd position will be x of 2 and x of 6. Similarly the odd will be, again this is 0th position, this is 0th position, this is first position, this is second position, this is third position. Again you divide into even and odd. So now it will become x of even function x of 1 and x of 5 and x of 3 and x of 7. Okay, so until you get 2 point DFTs are obtained, you can continue the decomposition process. This is example for endpoint sequence. Okay, so until this is a basic butterfly structure, 2 point composition. This 2 point can be represented, the basic the decomposition may be either decimation in time or decimation in frequency. Okay, so decimation in frequency, for example, decimation in time FFT will, if you take, this can be the 2 point. Okay, finally the 2 point can be represented, the computation can be represented this is for example A, B, this is a basic butterfly structure. I will explain. The 12 factor plays a vital role. You have to compute 2 complex multiplications and additions. So A is equal to what and B is equal to, so this I will explain later, WNB A, this is A plus WN into B, and B is equal to this A minus WNB. So this is a basic 2 point computation. This is a basic 2 point computation. Decimation in 2 point, decimation in time FFT, butterfly. Since it looks like a butterfly, this is a butterfly structure. So, the mathematically how it was decomposed, we will see the derivation now. So, how the input sequence are divided into odd and even, again how the endpoint DFT is decomposed into 2n by 2, again the 2n by 2 is divided in the same way into the 4n by 4 point DFT. It will continue until 2 point DFTs are obtained. So, next one we will discuss about the important properties of DFT. So, the two before the derivation, how it is decomposed in decimation in time FFT algorithm and decimation frequency algorithm, we will discuss about the twiddle factor, because the twiddle factor only plays a vital role in the FFT algorithm. So, the important properties of DFT with respect to the twiddle factor, because the W power, we know the DFT equation x of k, which is equal to summation of n equal to 0 to n minus 1 x of n into W power n k. So, where W is equal to e power minus j 2 pi by n, e power minus j 2 pi by n. Okay, this is a twiddle factor. So, this is a twiddle factor. Twiddle factor W plays a vital role. Okay. The properties of, because the W power kn, the W power kn, it possesses a circular symmetry. Okay. The properties, the W power kn possesses circular symmetry, circular symmetry. Okay. For endpoint DFT, for endpoint DFT, W power k of endpoint DFT, W power k of n plus n, which repeats periodically, with the period n. Okay. So, that will the periodicity property. So, what is the first property? Periodicity property. Periodicity property. So many DFT supports so many properties, out of which already I told you the periodicity property and the symmetry property are very important. So, the periodicity property says that W power, okay, this is n, twiddle factor n point, W power k plus n, which is equal to W power, there is a periodicity property W power k. For example, n is equal to 4. So, W power k plus 4 n, which is equal to, this is n is equal to 8, n is equal to 4 for example, which is equal to W power k. So, k equal to 0 means W 4 is equal to W 0. If k is equal to 1 means W power 5, 4 plus 1, which is equal to W power 1. Similarly, okay, symmetry property. So, symmetry property also plays a vital role, symmetry property. The two properties are periodicity property and symmetry property. The symmetry property says that W par k plus n by 2. So, k plus n by 2 is equal to minus W n k. This is a symmetry property. We can prove this also. I'll prove this also, how it was. The symmetry property, W bar, that is n here, okay. K plus n by 2 is equal to minus W n k. So first we will prove that. So for example, n is equal to 8. So how you can write? So n is equal to 8 means W power n k plus n is 8 by 2 k plus 4, which is equal to minus W n k. Okay, now k equal to 0 means, so W n is 8, no, k plus 4. So k is equal to 0 means 4, which is equal to minus W n 0. Similarly, k is equal, this is k equal to 0. K is equal to 1 means W 5, which is equal to minus W, this is 8, 1. Similarly, k is equal to 2 W 6, which is equal to minus W n, k is equal to 2 n 2. So it will go like this. So we can prove this one. This is important symmetry property. We will prove this. What is W here? You can write here. The proof you can write here. So what is W par? This is n by 2, no? N by 2 plus k, which is equal to, what is W? E power minus j 2 pi by n into n by 2 plus k, correct? So W par, what is W? So you can write W is equal to, what is W total factor? E power minus j 2 pi by n. You substitute that one, e power minus j 2 pi by n, n by 2 plus k. So which is equal to e power, you multiply this term, e power minus j, n will be cancelled, 2 will be cancelled, e power minus j pi into second term, when you multiply e power minus j 2 pi by n into k. So e power minus j pi, you can write cos pi minus j sin pi into e power minus j 2 pi by n into k. Again this can be written as cos pi minus j sin pi will be minus 1. So minus 1 into e power minus j 2 pi by n into k. So this can be written minus W par k. So you can write, so this is proved. W power n by 2 plus k or k plus n by 2 are same only, which is equal to minus W k. This is a symmetry property. So because of this symmetry property, the even sequence, odd sequence we are splitting. Because of this symmetry property, even though it will be calculated for n times, for k vary from n times, for k, what is the equation? For k varies from, for k varies from 0 to n minus 1, the k varies from 0 to n minus 1, each summation only needs to be computed n by 2 times. So, although it needs to be evaluated n times for k varying from 0 to n minus 1, each summation only needs to be computed n by 2 times for k varying from 0 to n by 2 minus 1, because this even function and odd function are repetitive with the interval of n by 2, because of periodicity property. So that the original DFT time is reduced by approximately 50%. Okay. And we are restricting the k value to the range only 0 to n by, the k varies from 0 to n by 2 minus 1 only. So which can be rewritten in two parts, odd and even part. So the first half, one part for the first half of the frequency points and the other part for the second half. So how you can write this equation now? The x of k can be written. So this x of k I will write. So the x of k now, I will write it here. The x of k now, because the k vary from 0 to n minus 1, but each summation needs to be computed only for n by 2 times, for k varying from 0 to n by 2 minus 1. So the first half you can restrict the k value to the range 0 to n by 2 minus 1. Again it can be rewritten in two parts. Okay, the first half of the frequency points and the second half also. So x of k you can write, first x of k we are dividing into even part and odd part. Okay, so the total factor will be w per k. So the k value we are restricting into n by 2, because of the periodicity property we are x of k plus n by 2 or n by 2 plus k. Okay, that is equal to your even term. The because of this property, periodicity property, that is a symmetry property. Okay, you can write minus w per k into OK, that is a odd function. Okay, for k is equal to 0, 1, 1, 2 up to n by 2 minus 1. We are restricting this k to the range, the k range, we are restricting the range, k range from 0 to n by 2 minus 1, n by 2 minus 1. So can be rewritten into two parts, even part and odd part. With one part for the first half of the frequency points, the other parts will be the second half of the points. So mathematically how we can divide the decomposition. Okay, so if you see the develop the decimation in time algorithm for n is equal to 4. So n is equal to 4, simple develop decimation in time algorithm for n is equal to 4. So x of k, for example, the n equal to 0 to n minus 1. So x of n w per n k, you know that the DFT equation. Okay, so this is Wn. So n is equal to 4. So if you write n is equal to 4, n is equal to 0 to 3 x of n into w4 nk. So Wn is equal to e power minus j 2 pi by n. Okay, so you split this equation into odd and even terms. So only x of 0, x of 1, x of 2, x of 3 splitting the equation into x of 0, x of 2 and x of 1 and x of 3. So, x of k can be written as the summation of n equal to 0 to, you are restricting your k into n by 2 minus 1. So, here x of 2n w4 is a 2nk plus the summation of n equal to 0 to n by 2 minus 1 x of 2n plus 1, that is a 12 factor w4 2n plus 1 into k. So, now you can split this one. This simple concept it is easy to understand. For n is equal to 4, 0 to 4 by 2, 2 minus 1, 1. So, x of 2n, okay. So, w4 2nk plus the summation of n equal to 0 to 1 x of 2n plus 1 into w for 4 2n plus 1 into k. So, now you can write so 0. So, k equal to 0, for example x of 0 will be this is a first part, this is a second part, okay. So, if n equal to 0, this will be 0, k number 0 1. So, what is the symmetry property says that f1 of k plus n by 2. So, this is x of 0 is equal to f1 of k plus the 12 factor w4 k into f2 of k. X of 1 will be x on this will be 0, f1 of 0, f1 of 0 plus w4 0 into f2 of 0. In k, in f1 if it is 1, then f1 of 1 plus w bar 1 as a 1 12 factor f2 of 1. Similarly, for x of 2 will be f1 of 2 plus w the 12 factor f2 of 2, okay. Similarly, x of 3 will be f1 of 3 plus the 12 factor f3 f2 of 3. So, what is symmetry property now? Symmetry property says that it is equal to f1 of k plus n by 2 which is equal to f1 of k. Similarly, f2 of k plus n by 2 which is equal to f2 of k. So, for k equal to 0, n is equal to 4, k equal to 0 you take. So, f1 of k plus 2. So, normally k equal to 0, k plus n is equal k plus 2 is equal to f1 of k. So, f1 of k equal to 0 means f1 of f1 of 0 equal to f1 of 2. Similarly, k equal to 1 means f1 of 3 will be f1 of 1. So simple 4-point computation. So in a similar way, we will do for n is equal to 8-point DFT. So each decomposition stage will be doubles the number of separate DFTs. Okay. So in this next section we will discuss about the 8-point decomposition in detail. Okay, how it is reduced. Thank you.